Okay, this is nuclear chemistry, the last unit, lesson 1. We're going to talk about how nuclear stability is determined today and what the difference is between natural and artificial transmutation. So, the stability of nuclei. Large atoms, meaning elements with atomic numbers greater than 83, are naturally radioactive and they are unstable. And it's due to the ratio of and this should say neutrons to protons, not the other way around. So make this correction, neutrons to protons being given off. They have no known stable isotopes, so they are continually decaying. So what we're going to see is as we get away from a 1-to-1 ratio in neutrons to protons, the stability of the nucleus becomes more unstable. Now, this can also depend on the particular element. For example, in smaller atoms, the neutron to proton ratio is 1-to-1. So therefore they are stable if the atomic number is less than 83. But there is an exception to the small atom rule. When an atom's mass is not its typical mass, meaning we have an isotope, a mass that is not seen on the periodic table, then the atom will be radioactive or unstable. So we always want to be looking at our periodic table while we're calculating the neutron to proton ratio. Radioisotopes, table N is also a really good source of information because it lists any element that is automatically unstable that you need to know about. So over here, and you don't have this chart in your book, you see what's called the band of stability. So the red line is when elements have a 1-to-1 ratio, neutrons to protons, and therefore they are stable. Now, this band of stability is when the neutron to proton ratio isn't exactly 1-to-1, but it's still considered stable. So with larger atoms, the neutron to proton ratio might not be 1-to-1, but maybe it might be like 1.4 or 1.5-to-1, and it's still considered stable. So you're not going to have to worry about this band of stability in Regents Chem, but I do want you to know that it exists. We talk about this more in depth in the upper level. We talk about this more in the college lab, in the college class. What you need to know specifically for Regents Chem is any atom less than 83 will be stable unless you're dealing with an isotopic mass. So, for example, in this first one that you see here, calcium 2037, if we look at our reference table, we know that calcium normally has a mass of 40. It normally has a mass of 40. So, in this case, the mass is 37, but we're dealing with an isotope. So I can tell you right off the bat this is going to be unstable because I've got 20 protons and 20 minus 37 is 17 neutrons. So this is going to be 17 basically divided by 20, which is going to give me a 0.88-to-1 ratio. So this is going to be unstable. I'm going to put a U for unstable. If we were dealing with regular calcium, the mass would have been 40, the atomic number would have been 20, and 40 minus 20 is 20, so 20 divided by 20 is 1-to-1. It would have been stable. Okay, let's look at hydrogen. What do we know about hydrogen? Well, hydrogen has 1 proton, and its atomic mass is 1. And it has no neutrons. So hydrogen is basically the exception to the rule. Hydrogen is going to be stable. Its mass is 1, and it has 1 protons, and it has no neutrons. So it's stable. Oxygen has a mass of 16 here. We know that we have 8 protons. 16 minus 8 is 8 neutrons. So this is 8 divided by 8, which is going to be 1-to-1. So this is going to be stable. Now this, obviously you can know that this is not the regular mass of oxygen. This has a mass of 14, so I have 8 protons, 14 minus 8 is 6 neutrons, so this is going to be 6 divided by 8. So this is going to give me 0.75 to 1, so this is going to be unstable. And the last one is neptunium. It's got a mass of 237. So that means it's got 93 protons, and 237 minus 93 gives us 144 neutrons. 144 neutrons. So what that means is I've got 144 divided by 93, and that gives me a ratio of 1.55 to 1. So here we see the atomic mass, atomic number is greater than 83. This is automatically going to be unstable. So what happens if I have an unstable nucleus? That means it will naturally decay. It's going to keep decaying, releasing some type of nuclear particle, turning into another element until it reaches a stable state. So that brings us to transmutation. Transmutation is the changing of a nucleus of one element into the nucleus of another element by gaining or losing nucleons. Remember, nucleons has to do with those things in the nucleus, so protons / neutrons, as it decays into a more stable state. So let's look at natural transmutation. This happens with unstable atoms, elements with atomic numbers greater than 83. So we want to use table N when we're writing decay equations. Use table N for decay equations. So here you've got uranium-238. If I go to table N and I look this up, I see the decay mode is alpha. So it's going to happen on its own. I put uranium-238 alpha. Remember that this is an equal sign. What I have on the left, I must have on the right. So if I have a mass of 238, so that means this has got to have a mass of 234, because 234 and 4 is 238. And then I have 92 on the left, so this is going to be 90. So now I go to my periodic table and I look up element 90 and I see that it's thorium. So this is what this element transmutated into. And we can have different types of natural transmutation. We can have alpha decay, beta decay, positron emission, electron capture, and this happens in the sun as well. Now, how does natural differ from artificial? Natural happens by itself. Artificial means it's induced. In artificial, I'm starting with something very stable. Neutron to proton ratio 1:1, and I'm going to bombard it with a high energy particle, and I'm going to smack it hard and cause it to transmutate into something else. So here I've taken nitrogen, atomic number 7, mass of 14. That means I've got 7 protons, 7 neutrons. It's 1:1. It's stable. I'm going to bombard it with an alpha particle. So this new mass is going to be 18, because remember, this is like an equal sign. I got 18 in the mass. I need 18 here. This is 9 here, so this is going to be 9. So this is going to turn into, believe it or not, this is going to turn into fluorine. So in natural, we have 2 reactants normally. I'm sorry, 1 reactant. We have 1 reactant and 2 products. And in artificial, we have 2 reactants. And normally it's 1 product, but can be 2. And that's because sometimes the element that it's changing into might give off an extraneous nuclear particle like a neutron or something. Okay, so types of radiation. We have alpha decay. And The source is naturally occurring elements. Its notation is 4,2He because it can be a helium nucleus, or it could be 4,2 alpha. It has a mass of 4. No external hazard. Shielding needed. What that means is basically this has low penetrating power. Low penetration, okay? Can pass through skin or paper. Beta particle, B minus or E. This is like an electron, so it's either written as 0, -1 E. Sometimes it's written as 0, -1 B, or sometimes it's even written as B minus, as you see here. It has 0 mass. It's dangerous internally and externally, and it can pass through cardboard or tin foil. Positron is simply a positive electron, so it has the opposite sign and charge, so 0, 1 E, B positive, or 0, +1 E. Dangerous internally and externally. It has no mass and can also pass through cardboard and tin foil. Gamma rays, no mass, no charge. So usually written as 0, 0, or as you see here, that was a bad drawing. Pen slipped on that one. So 0, 0, mass is 0. Very dangerous. This is the highest penetrating power, and this can be equivalent to X-rays. So just a nice little introduction there, and that's it for tonight.